So all we need to derive this reduction formula is the method of integration by parts. And in fact, if you want to go back to our last lecture and compare it to how we just did the integral of x times e to the x, or the integral of x squared times e to the 6x, you'll see that we're going to set it up in the exact same way. So what have we got here? We've got a product, which of course in of itself does suggest integration by parts. We've got a power of x, and specifically a natural number power of x, and we've got an exponential function. We can integrate both of those expressions, but in terms of which one gets simpler when we differentiate it, well, e to the x is its own derivative, so it certainly doesn't get any simpler, whereas x to the n gives us increasingly lower powers of x, so it's the better choice there. So yep, we're going to use integration by parts. And we'll do it by letting w be x to the n, and by letting dv be e to the x dx. So just like usual, dw then will be the derivative of x to the n, which is n times x to the n minus 1 dx. And v is the antiderivative of e to the x, which is e to the x itself. So the integration by parts formula tells us that the integral of x to the n times e to the x is v times w, that's x to the n times e to the x, minus the integral of v dw. So let's see, that's going to be e to the x times n times x to the n minus 1 dx. And we're almost there, because, well, n, remember, is a constant. We don't know what constant it is, but it's definitely a natural number, so we can factor that out. And that'll leave us with x to the n minus 1 times e to the x. So there we go. There's where that reduction formula comes from. They're not always quite as straightforward as this. A number of reduction formulas involving trigonometric functions, for example, do require the use of trigonometric identities in order to come up with the right expression, but they always start with integration by parts. So now how would we make use of this? Well, basically, what this reduction formula lets us do is it lets us apply integration by parts without having to formally set it up again and again and again. So the specific one that we want to work out here, the integral of x cubed e to the x. Well, the first thing we'll do is apply this integration by parts, this reduction formula that we've obtained here, observing that n is going to be equal to 3. So plug n equals 3 in here. We're going to get x cubed times e to the x minus 3 times the integral of x squared times e to the x. And we're going to keep using this reduction formula until we get to the point where we don't need it anymore. In particular, until we reach the point where we wind up with an elementary integral. We haven't reached that stage yet, but the integral that we have obtained here, it also fits the form of the reduction formula, just now with n equal to 2. So that's going to be equal to the x cubed e to the x carries over, as does the minus 3. But instead of multiplying it by the integral, if we apply the reduction formula with n equal to 2, then that's going to give us x squared e to the x minus 2 times the integral of x to the power of 1, so this x, times e to the x, which still isn't an elementary integral, but is still in the form of the reduction formula, now with n equal to 1. So let's clean that up a bit, and then we're going to apply the reduction formula one more time. So that's x cubed e to the x minus 3 times x squared e to the x plus 6 times the integral of x times e to the x. And then using the reduction formula with n equal to 1, we're going to get x cubed e to the x minus 3x squared e to the x plus 6 times x to the power of 1 times e to the x minus 1 times the integral. Well, now x to the power of 1 minus 1 is x to the 0, which is 1, so that power of x goes away, so we're just left with 1 times e to the x dx. And there we go. That is an elementary integral. So we've got x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 times the integral of e to the x. We don't need the reduction formula anymore because that's just one of our common integrals. So we get x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6e to the x plus c. And so there we go. There's our integral. It's exactly what we would have gotten if we didn't have the reduction formula to hand, but we just started off with our original integral, started off here, applied integration by parts, we would have gotten this. Then we could have applied integration by parts to this again, would have brought us here, applied integration by parts here, would have gotten us here, and then again we would have integrated the common integral to get our answer. So the reduction formula just kind of automates that process of setting up integration by parts in that very systematic way again and again and again. And you can see how that would be particularly beneficial if that was a really big power. If we started out not with x cubed e to the x, but suppose we started out with x to the 30 times e to the x. We wouldn't want to have to set up integration by parts 30 times. But using a reduction formula that many times, well, that's a bit less onerous. Now, you're not going to be expected to memorize any reduction formulas. Any reduction formulas that you would be asked to use in a test or a final exam situation would be given to you. They tend to be pretty lengthy expressions, certainly not something you'd want to commit to memory. All right, and so that finishes off Unit 1. So, in our next video, let's talk a little bit about where we're going to go in Unit 2.